In this tutorial, I will show you how to use truth tables to determine the type of a proposition. By type, I mean the profile the proposition has as far as its overall output values in a truth table. So let's start with that. If you think about a standard truth table, we're going to have variables like P and Q over here, and we're going to have some expression here. When we do all of the calculations and we finally arrive at the overall output value, there are three possibilities for what will be in this part of the truth table. One possibility is that it's a mix of trues and falses. That could be one true and the rest false, all the way to one false and the rest true, or any combination in between. The point is, there's a mix. The second possibility is that there could be all truths. In other words, no other value is output by the expression other than false. And that, of course, suggests the final option, which is that the expression yields all falses. These are our three types then. For an expression that yields a mixture of trues and falses, that expression is called contingent. All trues is a tautology. We've run into that before. And all falses are contradiction. So that's our goal. Our goal will be to determine the type of proposition. So now let's look at a few examples. What I'll do here is I'll create a new page for us. Now let's consider an expression like P implies not P or Q. So now if we do a truth table for an expression like this, we'll just do a standard truth table. So we have two distinct variables, P, it's used twice, and Q, which appears only once. Now in this expression, we want to determine the scope order. So this is our level 1 operator. It branches two ways. Over here, we just have a variable and no operator, so it terminates. Over here, the operator of largest scope is the OR, so that's our level 2 operator, and we have two branches. Q terminates, but over here we have not P, so that's our level 3 operator. So what we're going to do then is once we fill in the truth table, we will start calculating the output values for these two expressions based on their inputs. Obviously, we have to start with the operator of smallest scope. This is, again, what we mean by working from the inside out. So we'll calculate the value of this level 3 expression first. So for the first row, if P is true, not P is false, not false makes true, not true makes false, and not false makes true. So there's our 4 rows. Next, we go up to the level 2 operator, P, not P or Q. So we have the value for not P already for each row. We just need to pick up the value of Q from over here and use OR to determine the output. So false or true makes true. True or true makes true. False or false makes false, and true or false makes true. So we're finished with this row, and we've completed our level 2 operator. So now we look at the level 1 operator. So P implies all of this expression, which is represented by these values here. So on the first row, we have P is true, and the output of this whole expression on the right-hand side is true. So true implies true is true. P is false in the second row, so false implies true is true. P is true in the third row, but this expression yields a false for that row, so true implies false is false. And for the final row, false implies true yields true. So this means that the value of the whole expression here is given under the level 1 operator. So that's this. Now notice, this is a mixture of trues and falses. Yes, we have one true, one false and the rest are true, but that's still a mix, right? It's not all true or all false. So this expression then we would say is a contingent proposition. Okay, great. Now let's look at an example of a one of the others. So let's look at an extremely simple example. How about P is equivalent to P? It's a very, very simple truth table, but it illustrates exactly what we're talking about here. So we have exactly one variable, P. It has two instances, obviously. So that means we're going to do 2 to the first power is only 2 rows, so that's true and false. And when P is true and is equivalent to true, we get true, and false equivalent to false for the second row, we get true. So this is an example of a tautology. In other words, this truth table as a whole shows that this expression can only yield true, no matter what the two inputs are for each of these rows. Okay, by the same token, let's do a truth table for this really simple expression. P is materially equivalent to not P. So now if you think about this, what we're going to have here, we have one distinct variable, so that's P. So again, we're going to have only 2 rows. There they are. So now we have a level 1 operator and a level 2 operator. So in the level 2 operator, let's do the negation. So if P is true for the first row, not P is false. Second row, if P is false, then not P is true. Now let's do the material equivalence operator. For the first row, P is true and not P is false, so that yields false. And in the second row, P is false and not P is true, so that yields false. So now we're finished with this expression, and you will notice that no matter what the input is for each of these rows, P is equivalent to not P yields false. So that means that this expression is a contradiction. Okay, so now what we've learned here is how to explore these types of proposition and actually how to determine the type using a truth table. So what you should do next is practice, like look up some expressions in the handouts or in the textbook and construct truth tables and see if you can determine what type proposition you're dealing with based on how the truth table turns out. Again, it will turn out either all falses, in which case you have a contradiction, all trues, in which case you have a tautology, or it might turn out to be a mix of trues and falses, as we saw in that previous example, in which case it's a contingent proposition.